Another fun week has gone by in my self-teaching, self-learning phase for real analysis. So now I finished working through the best that I could, Chapter 4 problems. Could have done a little more, but I wanted to get going with Chapter 5. And as I've said before, in the self-teaching phase, I'm more in the reading than in the doing problems, but I'm doing enough problems because I gotta figure out, I gotta learn something. I can't just like write out the book to my notes as if I was writing in some foreign language, that doesn't work. So I am now up to, I'm doing problems for section 5.1. Just getting started, had a lot of fun with one of them early this morning. And I'm well into chapter 6, and chapter 6 is shorter. It's about infinite series. And so actually I'm kind of almost done with chapter 6, which is nothing like what happened with chapter 5. Chapter 5 took forever to read, and I think I'm probably going to be doing problems for chapter 5 for 2 weeks. Came across a very interesting proof while reading in chapter 6, and it's, let me see if I can get it right in here. It's Abel's formula, and I love the way Wade did this. I mean, it's really well explained, and what I love the most is that he talks about how this formula is sort of like integration by parts, but for series. And I thought, well, that's a great way to explain it, So yeah, it says it right here. In this context, Abel's formula can be interpreted as a discrete analog of integration by parts. I was like, okay, wonderful. And so I was going to try to do the same thing that I did for the indeterminate forms of L'Hopital's rule. It's like, hey, I want to go through all the other books that I have and, compare and contrast. Maybe I'll make a video about this comparison and contrasting. No way. And this particular proof and the way Wade explains it is a great example of when you go down the self-teaching route, or even if you take a course and you really want to get into a subject, you better have more than one book. And so I went through my dozen analysis books, and I actually keep buying a new one every other week. And at some point I'll show I think I'm evolving to an analysis shelf, just a shelf of analysis with notebooks and books. It's where this is going, folks. It's a deep subject. But yeah, I looked through, and Rudin, a couple other books, they just have like Abel's formula, and then the proof, they basically say, well, you start from this and you end here and you're done. Bye. And so TBB, the novel, the Dickens book, had a lot of series discussions, and I'm going to show that at some point after I do a lot of series work. But yeah, definitely Wade just like hit it out of the park. Nobody else explained this the way Wade did. So way to go, Wade. And then where I left off last time, I was finishing chapter 4 problems. But I had only done, these notes start at page 104 for problems. I usually put a P in front. And I think I was like at 121 when I left off last time. And then the end of chapter 4 goes all the way to 152. So I did a fair amount of trying, maybe some succeeding. Came across a very interesting problem that I may show in a Desmos video. Not sure if I want to torture folks with a Desmos video, but I may do that. And yeah, sure enough, had a lot of fun just going through, and I think I got this problem right. Just x to the m over n. Yeah, differentiating it. So yeah, sure, had a lot of fun with chapter 4 working through these problems. Still early stages. Definitely a course would help me tremendously. Yeah, here it is, comparing various functions, and in this case it was comparing e to the x to x to the n, and then log x to x to the n. That got very interesting. Yeah, that got very interesting. Oh, here it is. Yeah, here it is. That's right here. And so I kept plotting in decimals, and it's just things that I had never really realized about x to the n. That when you go x to the n very high numbers, it just becomes almost like a sideways delta. Not delta, but just a straight line. And also, as you're flipping back and forth with the odd and even powers of x when they're natural numbers, the odd ones will be like x to the cube and will have a negative part. But then the even ones will have it, of course, they're even. X to the square, x to the 2, x to the 4, 6, 8. They're all like that. And then as they go very high, it looks like a bucket. And as you go very high on odd, it just looks like a, a weird, this weird thing. Yeah, it was just very interesting how, and then when you modulate it with a constant, when you modulate, what was it, x to the n with a constant, then you're sort of having the two graphs dance around each other, see how close they get and how far away they get. So yeah, very interesting, and I may make a Desmos video about it and torture some folks with it. Yeah, that was great. That was a lot of fun. Of course, I love calculus, so it's easy to say that I'm having fun. And then when it comes to progress for my reading, of course, in blue I always draw out the current week. This is the current week, so I'm 6 weeks in. I'm still a month ahead in reading, and I will continue to do that because I've got some vacations in here that'll slow me down. And then, of course, for reading, I am section 6.4. I'm doing about a section a day in the mornings. And then for problems, I kind of chickened out on section 4.3 and 4.4. I could have done more, but I really want to get going. And so, yes, I want to get back to these. I'm not sure when I'm going to go and do like a review. I'm not sure that I will, frankly. I don't want to look in the back of Wade. I don't. I want to wait until I take the class to start looking in the back of books for answers. I think that I'm going to hold out all the way till then. Then this is the glorious chapter 5. And yeah, I had a lot of fun. I mean, these are things that we have all taken in calculus. But now, done with Riemann sums, upper integrals, lower integrals, a lot more rigorous as analysis should be. And yeah, pretty cool stuff. Partitions, lots of partitions, refinements on partitions. Mean value theorem. Then, of course, the core. When you take a calculus course, this is like the main thing, the fundamental theorem of calculus. What integrals are all about. Change of variables, for which Wade did a great job in the proof, I believe. I think, very interesting proof for change of variables. I found a paper written about change of variables, and it was very similar to the way Wade did it. And so I was like, yeah, I'll put it in. I mean, it bulks up my notebook, but the terminology is very similar. It almost reads like the section, but it has references, and it shows how I believe what Wade used. He must have used something like what's detailed here, the people who made these proofs. Kestelman, Davies. And so they're actually fairly modern proofs that Wade went out and put in his book. I commend them for that. That's pretty novel in my book, and reminds me of Rosen. Rosen did this for number theory, and that was very elegant and useful, I believe, as a student. I found it to be. Additional reading, generalization of Riemann integral, improper Riemann integration. Yeah, lots of really interesting content. Then functions of bounded variation, which ended up going into convexity, some convexity discussion. Interesting, very interesting, convexity. Then I found, and this is all near the end, Jensen's inequality, which is very well explained in a handout that I found, where this person talks about a simpler way, which is kind of obvious when you read it, about, you evaluate the curve if you evaluate the curve at the middle and it's concave, that lower value is going to be lower than the average of the endpoints that you pick at the higher point, and vice versa when you flip it and you make it concave. So yeah, more fun handouts just to have fun reading over time as I review. And I'm going to do multiple reviews, I'm sure, at some point as I take the course, including going back to these notes. So yeah, there's chapter 5. And I've started working on chapter 5 problems. Just got started.